Okay, so we've done that, and by that algebra, um, writing C0 in terms of C1, and just working through it, we pick up these phase factors, these e to the I Ka terms, giving us both what we called at the end of the last lecture, that's the self-energy terms that show up on the corner of the 3x3 diagonal here. There's two new terms on the corner, and the inhomogeneous terms out there on the right. And they're related. We showed that the imaginary part of the self-energy was just 1/2 of that h bar v over a on the right. So that h bar v over a is gamma, what we call gamma, and the imaginary part of the self-energy is gamma over 2. The imaginary part of these corner terms circled in red in the matrix itself. Like that, and that's really a basic definition actually. This is true no matter what's giving rise to that self-energy, whether it's due to the contacts or due to some scattering mechanism like phonons. And then we went through and discussed in detail the fact that this is not Hermitian because of those imaginary terms on the corner blocks, and exactly what that physically means in terms of finite lifetimes, etc. And at the end of the last lecture, we, for the first time, defined what we mean by a retarded green function. So we start off with this 3x3 matrix, E minus H, H sub D for that, what we call the device part of the Hamiltonian. By truncating it, we pick up these new terms, which we call the sigmas. And if we write sigma as a full 3x3 matrix, it just has these two corner blocks down there in the lower left. And so if we then write this 3x3 matrix formally as E minus H sub D minus sigma, then our equations for the wave functions in the device are given by this in red. And this would be the solution for C1 through C3 due to injection from the left. Similarly, you get the same thing for injection from the right, just changing the right-hand side vector from what it is written here to just 0, 0, I gamma over I gamma sub r. That would be the only difference. And then you have the wave C1 through C3 due to injection from the right contact. And so the matrix on the left doesn't change, and by definition that matrix is the inverse of the retarded green function, because excuse me, it gives the impulse response of the system to any input. So right now, the input is just due to input at the leads, these gamma L's or gamma R's. And for the electrical engineers, this is what we call in Laplace space H of S, the impulse response of your circuit. Right? H of S was the impulse response of your circuit. If you hit it with a delta function input, H of S was the response. That ring a bell? From like first year circuit theory, H of S. Okay, well, G of E, function of energy, that's your impulse response of your quantum system. So if you hit it from the left lead with that right-hand column vector, you get C1 through C3, that's your impulse, that's the response. If you hit it from the right lead with gamma R, you get wherever you hit it. Later, when you do phonons, you can hit it somewhere in the middle of the system with a phonon, and it gives you the impulse response to some phonon scattering event in the middle of the system. But right now, the only way we're stimulating the system is by sending in something from the contacts. So this is, and then formally at the bottom, that is a formal solution, right? Your wave function in the device is just retarded green function times whatever you're injecting from the leads. And that's where we ended last time. Okay, so, and to get to that nice ending, I had to skip something, so we'll go back and do that now. We claimed that by doing this algebra, manipulating the matrix like we did, just by solving the 3x3 matrix, it gives us the same solution for those 3 sites in your device that you would get if you solved the whole infinite system. Okay, and so now what I want to do is show that that is indeed true. Okay, so what we're going to do is consider the full infinite system where there's no variation, every site energy is the same, so it's just an ideal crystal. And we're going to go through this algebra and show that you get the same states you would that we got in 208, because we know the solution of the wave function for this tight binding model of a crystal from 208. So we're going to first consider a left injected wave. And we know the exact solution, right? So for this ideal chain, one-dimensional chain, the exact solution is just C sub n. I mean, it's a plane wave, right? And we aren't going to worry about normalization. E to the I, Ka, and we'll just choose our phase factor like this. The same way we did when we set up our scattering states. Right, that is, we know the solution. So what we're going to do is see that if we put in this solution for our truncated 3x3 system, all the 3 equations, because we got a 3x3 matrix, the 3 equations corresponding to the 3 rows are indeed satisfied. All right, that's what we're going to do. Before we do that, let's see. So, and specifically in our device, it means that the vector we're going to put in to check is C1 equals 1, right? C2 is e to the I Ka, and C3 is e to the I 2Ka. So that's the vector we're going to put in and see that the equations are indeed satisfied. And before doing that, we're going to rewrite this corner term. So the corner term, the 1, 1 term of our matrix, E minus H minus sigma, was E minus epsilon minus T E to the I Ka. That was our 1, 1 corner term where K was K left. And it was exactly the same for the bottom right corner term too, where K would be K right. These are our corner terms. But it's going to be convenient to rewrite this using the dispersion relationship. E is equal to epsilon plus 2t cosine Ka, which is equal to epsilon plus T e to the I Ka plus T e to the minus I Ka. Did I get that right? Yeah. Which means that putting that back into, so if we put this back into the expression, that we have for our corner term, our corner term becomes e minus epsilon minus t e to the I ka is equal to t e to the minus I ka. Right, so our corner term is equal to that on the right-hand side. Which just makes the matrix a little simpler. Okay, so putting this into the corner term, we now need to check that this solution I wrote for that this known solution for C1, C2, and C3 does indeed satisfy the equations that we came up with. So we need to check that t e to the minus I ka, and this is just an ideal chain, so k is the same everywhere, right? K left and k right are the same. Minus t, 0, minus t, e minus epsilon, minus t, 0, minus t, t e to the minus I ka times the vector 1 e to the I ka e to the I 2ka is equal to the right-hand side. So this is what we're checking. Find out if this is true. And I'll write this, my gamma, out according to its definition. I h bar v over a 0, 0. Right, that's what we need to check. See that that is indeed. And so we're just going to check row by row to understand whether these equations are indeed true. Right? This is 3 equations, and we just need to see that each equation is actually correct. So let's look at the first row. So the first row, I'm just going to have t e to the minus I ka minus t e to the I ka is equal to I h bar v over a. So we got to check to see if that is indeed true. And so the left-hand side, this is minus I 2t sine ka which is equal to I h bar v over a. So this is indeed correct. So the second row, what do we got for the second row? So this is just minus t plus e minus epsilon e to the I ka minus t e to the I 2ka is equal to 0. All right. And so if we multiply through by e to the minus I ka, if we multiply and then multiply the whole thing by e to the minus I ka, all right? And so that'll, and so then we have minus t e to the minus I ka plus e minus epsilon minus t e to the plus ika equals 0 if we do that. And this is simply the tight binding dispersion relationship, right? You combine the two t terms, and this simply rearranging, you have E is equal to epsilon plus 2t cosine Ka. So this is also true. So the second row is also correct. And the third row, what do we got for the third row? The third row simply states that well, this is trivial. We just do the multiplication. You don't even need to do anything. Minus t e to the ika plus t e to the ika equals 0, and we don't even need to do anything there. That's the third row. Third row. Just doing the multiplication. All right, so this does indeed give you back the exact solution that we would have calculated in 208. And while we're at it, we should check just to make sure everything's good. If we inject from the right, the plane wave amplitudes for the left moving wave are C sub n equal to e to the I Ka 3 minus n, choosing my phase like that. And so I've got C1 is e to the I 2 Ka. C2 e to the Ika. C1 is 1. Or C3 is 1. So that's the vector I'm going to put in for the right-hand side again. Again, I write out my equation. It's the same matrix as before. That never changes. Now I've simply got e to the I 2Ka e to the Ika and 1 equal to 0, 0, I h bar v over a. And I've sort of just, the top row, I've sort of just permuted the equations in a way, right? I mean, I flip the vector upside down, the C vector upside down, and I flip the right-hand side upside down. So it should be pretty obvious that everything's going to hold. Let's see, the third row, I'm just going to get, this is a minus t, and what I guess I had a t e to the Ika here, I believe. Where's my matrix? Yeah, or minus Ika, t e to the minus Ika. T e to the minus, so that's my third row. So the third row, I've got for the third row, I've got minus t e to the Ika plus t e to the minus Ika, which is my, again, going to give me the velocity, minus I 2t sine Ka which is equal to my right-hand side. The second row is just going to give me my dispersion relation again, just like it did before. And my first row will be trivially 0, just like the third row was before. So this is also true. Gives me the correct answer whether I inject from the right or the left. Okay, so now that we're all satisfied that doing this algebraic manipulation just does indeed give me the exact solution in the 3 by 3 part, our quote device part of the device region or device part of the Hamiltonian, then now we're ready to just start formalizing everything we've done and start cranking the machinery to generate, the full, at least as far as coherent transport is concerned, the full non-equilibrium green function formulation of these equations. Okay, so last time we ended with the definition of our green function, which was just the inverse of that matrix, and the formal, the formal solution C1, C2, C3 is just equal to this green function matrix, which is E minus H sub D minus sigma inverse times your right-hand side, say if you're injecting from the left. Right? We can write the solution fairly compactly. And so now let's, so far we've got the wave function in the device, but as engineers we finally want to calculate something like current. So let's now start talking about how we calculate the transmission coefficient, which is where the discussion started off, looking at these scattering states and the fundamental definition of the transmission coefficient. Okay, transmission and current. So, if we go back to our fundamental definition of the transmission coefficient, it's the transmitted flux over the incident flux. Right, that was our fundamental definition of the transmission coefficient. Now the incident flux was just our plane wave, like e to the I k, well in the continuous picture, e to the I k x times the velocity of the incident wave, right? That was our incident. Well, we got to take the wave function squared, but the magnitude squared of e to the I k x is 1. So the incident flux is just the velocity times 1. The transmitted flux was the outgoing wave function magnitude squared, the amplitude of that squared times its velocity. And so the ratio in our tight binding picture is the magnitude of the outgoing wave function, C3 squared, okay, that's the amplitude of the outgoing wave function, times the ratio of the velocities. Okay, this is injecting from the left. Okay. And we said that, whether you inject from the right or the left, this transmission probability has got to be the same. Otherwise, you violate some fundamental things. Oh, I'm sorry. So it would also be, okay, well, let's just stick with what we got, thinking about injecting from the left. So this is also equal to C3 squared times the ratio of the gammas. Right, because the gammas were related to the velocity of just h bar velocity over a. So if you take the ratio, everything cancels but the velocities. And now, let's go back and look at our formal solution for these C's. So we have C1, C2, C3. Yeah. Okay. Let's see. What do I need? C3. So I'm going to have all the elements of my green function here. G11, G12, G13. That row column. Oh, I'm messing up my indices. Sorry. It's row column, not. Let me try that again. So row 2, 1, column 2, 1, 3, 1. And then G row column 1, 2, G 2, 2, G 3, 2, and row column 1, 3, 2, 3, 3, 3. Right, that's the formal solution where, this G is just the inverse of E minus H minus sigma of that 3 by 3 matrix we derived, right? So this G is just the inverse, whatever that inverse is. And I just wrote it out element by element. So this matrix is our E minus H sub D minus inverse. It's the inverse of that 3 by 3 matrix that we've been looking at. It doesn't look very good. That's not an equal sign. That's supposed to be a -1. There. Okay. And so C3, in terms of our green function and gamma, just looking at this equation, C3 is equal to G31 gamma L with an I G31 gamma L, right? That's C3. And so putting that in for our expression for our transmission coefficient, we have T, I'll write it out again. We said it was C3 magnitude squared times gamma R over gamma L. And then substituting in this expression for C3 right above it, I get that that's equal to the magnitude of G31 gamma L squared times the ratio of gamma R over gamma L. And that's equal to the magnitude of G31 squared times gamma L gamma R. This is one of the more famous forms for the transmission coefficient. We'll come back to this in a second. Now if I go ahead and define a matrix gamma in the same way we defined our matrix sigma, as gamma equal to gamma L right, just a 3x3 matrix with two terms in it corresponding to the gammas of our two leads. Then gamma L is gamma 1, 1, gamma right is gamma 3, 3 in this matrix. And then just rewriting this equation that we just derived down in the lower right there in terms of these using the indices instead of left and right, I have that T is equal to G R 3, 1 gamma 1, 1 GR 1, 3 or 3, 1, sorry, 3, 1 star, I guess. GR 3, 1 star. GR 3, 1 star and gamma. So I just took the magnitude squared of G and wrote it as GG star and distributed it between the two gammas. Right, so GG star was that magnitude squared of G. The advanced green function, something we haven't talked about. Well, we did briefly. The advanced green function is GA as opposed to GR for the retarded. We have the retarded and advanced. When we were discussing this the other day, I said the retarded was the causal, the advanced is the anti-causal green function. And in the energy domain, in terms of energy, which we're working in, GA is equal to GR dagger, the Hermitian conjugate of GR. So you do the transpose and you take the complex conjugate and you go from GR to GA and vice versa. So what that means is that GA (1, 3) is equal to GR 3, 1 star. And so the final form, and I'm going to write this, which is the form you will often see it, is that T is gamma 3, 3 GR 3, 1 gamma 1, 1 wait a minute, I'm writing it backwards. Okay, I guess I can permute. Right, there's no problem. GA 1, 3. So I put the gamma 3, 3 in the front, and everything just follows in the same order, sort of cyclical permutation of the order. And I'm writing this with, if you notice, I got a 3, 3, 3, 1, 1, 1, 1, 3. All those matrix indices follow in order. Right now, this doesn't matter, but in general, all these terms will become matrices. Like if we have 2 orbitals per site, for example, or more than 1 atom per site. These would represent matrices rather than scalars. Everything, the way we've been doing it, everything is a scalar right now, so order doesn't matter. In general, order will matter, and this is the order that it will occur. And to get the full transmission coefficient, you would take the trace. This would be a matrix. You would take the trace of this, but I can cyclically permutate under the trace. So any cyclical permutation is fine. But the way you do a sanity check when you're deriving something is that these subscript indices always follow like this in order: 3, 3, 3, 3, 1, 1, 1, 1, 3, etc. Round and around. Yeah.
What's the permutation name you are calling?
What's that?
The permutation name you are calling cycling permutation.
Cyclical permutation. Cyclical permutation. It's just so in general, if these were matrices, I would be taking the trace of this matrix. So in general, I would have T is the trace of whatever matrix this represents. Gamma 3, 3, GR 3, 1, gamma 1, 1, GA 1, 3. And the thing about a trace is that the trace, you can cyclically permute under the trace. As long as they keep, as long as the order is preserved, ABC, CAB, and what would be the next one? BCA. So under the trace, you can cyclically permute your terms. You have to keep that cyclical order, though.
So, so later, this sigma 3, 3, these terms will become matrix as well?
Yeah, they'll all be matrices. Like when you have more than 1 orbital per site, if we had sp3, then there'd be 4 by 4 matrices. Each one would be a 4 by 4 matrix. The gamma, the G, so these would all be, so you have our 3 by 3 matrix we've been working with, but each element of that 3 by 3 matrix would be a 4 by 4. It'd be a block.
And we can include spin as well, I guess.
Be just multiplied by 2, so it'd be 8 by 8 in that case. And the trace would include the sum over spins. You can just think of spin as another two orbitals. We haven't got there. I like to, right now we're just dealing with scalars. You can combine everything. Order doesn't matter. But in the future, I like to immediately start writing it out in the way that it will need to be written out eventually. Because by keeping track of your indices like this, sometimes even when you don't need to, it prevents a lot of errors. I found the hard way. Okay. So this is our transmission coefficient. So this was all for injecting. So far we've been considering the case where we've been injecting from the left. Everything so far has been injecting from the left. And now let's look at injection from the right. Because this is going to give you most famous expression of all, what's called the Fisher-Lee form for the transmission coefficient. So if we inject from the right, I have that T is equal to C1 squared VL over VR. Just our definition, basic definition of the transmission coefficient. And writing the V's in terms of the gammas, that's C1 magnitude squared, gamma left over gamma right. And we do our usual, we go through the same exercise, so T is equal to the magnitude squared of G, retarded Green function, 1, 3, gamma L, magnitude squared, times gamma L over gamma R. Right, that thing in magnitude squared term is my C1 magnitude squared if you go back and look at the equation for injection from the right. So if we're injecting from the right, my right-hand side is my 0, 0, I, gamma over R. So we're multiplying that green function matrix by. Right. And so just replacing my left and right with the indices, I get that that's equal to, let's see what I got. Let's not jump since this gives you such a famous expression. And this is going to be gamma L gamma, I must have messed something up. Gamma right, this should be a gamma right in here. Inside this is a gamma right. Okay, so that, again, I get a G squared times gamma left, gamma right. And now putting in the indices, I get the T is equal to gamma 1, 1. GR 1, 3. Gamma, what are the indices on this going to be? Once you, it's got to be 3, 3. Gamma 3, 3. And GA, what are the indices on this?
3, 1.
3, 1. Once you know, these indices, you almost don't need to know what you're doing. Once you can just start writing down, they have to follow. And this form is extremely famous. This is known as the Fisher-Lee form of the transmission coefficient. All right, and this is the form that you see in most papers when they say, and we calculate the transmission coefficient, and they want to throw out some formula in terms of the green function and the gammas. This is what you usually see. Okay. And again, keep in mind, all we've done is manipulate our Schrodinger's equation to get here. And both of the, whether you use this expression or this other expression down here, it's going to give you the same answer, because transmission, if you inject either from the left or the right, you have to get the same transmission. Otherwise, you'd violate some fundamental properties, such as you'd have current flowing in equilibrium and stuff like that. So these two are the same, but usually the way people write it is like this. Okay, now what? That's great. So this is our transmission probability. So now, but what we want is current, right? It's not quite good enough just to have a transmission probability. What we really want is current. So, okay, so what is the current? The current is the charge. This charge, which would just be our Q, or charge of your electron, times the incident flux times the probability that the flux transmits through the device probability There's a probability that it transmits through the device. And then we also need some statistical factors that tell us whether the initial state was occupied or empty. And we'll get to them in a second. So let me just write down the expression. So the current is equal to, so here's my charge. I'll have my usual normalization factor for this, some length of the device, which, well, I guess it would be the length of the entire system, which we let go to infinity when we convert our sum into an interval. So sum over our injected wave vectors from the left, velocity, it's a second term in that thing up above. Our incident flux is just the velocity, right? The probability that it gets transmitted, well, that's our t for that incident wave vector, which you can convert into an energy. Times these statistical factors that you need to determine, if the state is empty, then obviously you'll get no current. So this, your Fermi factor on the left, so this tells you the probability that there's actually an electron there to transmit it. So E, the energy for that wave vector, minus the chemical potential on the left. Right? That's your Fermi factor for the left. Minus, and we'll talk about this in a second. Minus E, the same energy. Energy doesn't change. E of KL minus mu R. I guess it depends how you define that energy. We'll use the left as our reference. Okay, so there's two ways to think about this. So remember, whether you inject from the left or the right, the transmission is the same. Okay, we'll talk about the Fermi factors when we're done. First, let's just work on the transmission part and let these go along for the ride. So the first thing to do is convert from the sum into an integral, okay, like we always do. So that's equal to, my charge. That 1 over L will get absorbed when I convert my sum into an integral. So integral from 0 to infinity dk over 2 pi VL, and then everything just, so all we've done is convert. So nothing changes in the brackets there. I've just converted my sum into an integral. And then we now need to convert, because we work in terms of energy, we now need to convert this integral over k into an integral over energy. And so that's equal to the charge over 2 pi. So I'm just bringing the 2 pi outside the integral. That's just from above, the same 1 over 2 pi. This is part of the conversion, which I'm going to bring outside, 1 over h bar. And then integral dE dE h bar dk inverse. You can think of that as like my Jacobian or something, right? That converts a dk into from dk into a dE. And since I have an h bar in there, I put the h bar in there because that'll give me a velocity, right? That dE over h bar dk is a velocity. And since it's inverse, it's going to kill the velocity that's up above. Right? So that's going to kill this term. VL T of E times F of E minus mu left minus F of E minus mu right. Right, so that dE over h bar dk is 1 over velocity times the velocity. So the those two terms are just going to disappear. They're going to cancel each other. Right, so this cancels that. And I'm left with the final form, that J is equal to E over H integral dE T of E times F of E minus mu left minus F E minus mu right. And this is the final form that you see relating the transmission coefficient to the current for coherent transport. And you know, if your T includes spin, fine. If not, you would just multiply by 2 for spin. So that 2 is for spin if you haven't included it. Then you just throw it in by hand at the end. And so this is the classic expression you see for coherent transport. relating the transmission coefficient.
In the paper, isn't there a term E square?
It's for conductivity. You go from current to conductivity. Just wondering if we do that. It's a trivial step. Okay. I don't know if I do. I mean, it's such a trivial derivation. Okay, so remind me, seems like as good a time as any to do that. But before I do that, let me talk about these Fermi factors on the right-hand side, which I kind of just wrote down without. So often what you see for these Fermi factors is something that looks, and so let me just to cut down on notation. I'll define this guy as F left, and this guy is F right, so that I don't have to keep writing out the whole thing every time. So what you often see in the parentheses is I need to have, so this tells me that yes, the state on the left was the probability that it was filled, right? And then you say, but it has to go into an empty state, so I need to multiply that times this term, because it can only transmit if it goes into an empty state. And you have the flux going the other way, so I have stuff being injected from the right, but that has, equivalently, that has to go into an empty state on the left. And often you'll see that sort of expression written for the Fermi factors. Okay? So this term here, this is for injection from the left. And this would be for injection from the right. And the current would be, left minus right.
But which one is correct? I mean, the upper form of the lower form, or those two equivalent?
They're equivalent. Because for coherent transport, you're always at the same energy. So if we just write this thing out, we have F left. F left minus F left, F right, minus F right plus F left, F right. So these cross terms cancel, and you end up with what we wrote down up above. So for coherent transport, which is elastic, energy is conserved, they're equivalent. So this box written in red is the expression for coherent transmission, at least in 1D. We'll talk about when we go to more dimensions like finite cross-section and stuff like that later. But we're doing everything sort of in this simple 1D model right now. And if you had a finite cross-section, then you can handle that by each one of those terms in your 3x3 matrix becomes a block, and the block is sort of the size of the number of basis states in the cross section, and you trace over that, and then it looks just like this also. So this expression is the same as what you get for a carbon nanotube, where that T would now represent the trace over all the states in a atomic plane, or like this also works for a nanowire, where the T is a trace over all the sites in an atomic plane. We'll talk about that later. Okay, so that is current in terms of transmission. The other thing you need when you're doing device modeling is a charge density. Okay, so in terms of in our device, it means we need the values of Cj magnitude squared for sites 1, 2, and 3. We need Cj squared for j equals 1, 2, and 3. So, and we get Cj's, two different Cj's, one from injecting from the left and one from injecting from the right. Okay? So, for injection from the left contact, I get that Cj, I'll use a superscript, so we clear injecting from the left, Cj magnitude squared is equal to G sub r j comma 1 times gamma 1, 1 magnitude squared. If you go back and look at that matrix equation for the C's, right? C is equal to GR times I gamma. Well, I wrote it out as a matrix, but okay, so this is like I gamma 1, 1, 0, 0. So the if I do this matrix vector multiplication, this is just going to pick out the first column of G, right? So this is the first column of G. First column of the GR matrix. Right, row column. Those are the indices. So rows 1 through 3 and all the first column. So what you're getting, first column of G. And similarly, we also need the C's where I inject from the right. So from right contact. So from right contact, I'm going to get C, J, R magnitude squared is equal to GR. Anyone know what the indices are going to be here? What's the first index going to be?
3.
J.
J3.
J3, yeah, right.
J is obvious.
J, okay. Just want to make sure it's obvious. Gamma 3, gamma 3. Okay. Again, because now the right-hand side would be, 0, 0, I gamma 3, 3. And, if we, okay, let's just do that for now. Okay, so those are the two expressions for the C's, depending on whether I inject from the left or the right. Now, the occupation of these C's depends on where it was injected from. So the occupation of this state is going to be determined by F of the left lead everywhere. So the occupation of this state and the state that evolves from injecting, this plane wave from the left lead is determined by the Fermi factor of the left lead. The occupation of this state is determined by the Fermi factor of the right lead. These scattering states are eigenstates of the Hamiltonian, and an electron in a scattering state remains in that scattering state. It does not interact with any other state. So the occupation of this state is given by the occupation of the contact from which it originated. It's injected by this thermal reservoir corresponding to a contact. So the occupation of that state that evolves from that thermal reservoir is determined by the occupation factor of that thermal reservoir. So the contact from which it originated. So to get the electron density, I need to sum up these contributions. So N J is it going to keep doing that the whole time? Okay. NJ, due to injection from the left contact, is equal to 1 over L, sum KL. This is really annoying. Yeah, it's not that. I don't know what's going on. Sum KL. GRJ1 gamma 1 1 magnitude squared times F of E KL minus UL. Right, so I just weighted it by what's in the magnitude squared is my CJ squared, and I'm weighting it by the probability that this state is occupied. And I convert that sum into an integral, as we did before. So the integral from 0 to infinity, dk over 2 pi. Same deal in the, nothing changes in there. Same f out here. Let's convert my sum over k into an integral over k. And as usual, what we want to do is integrate over energy. So that's equal to integral dE over 2 pi. dE or dk sub L inverse magnitude squared of my G gamma times my Fermi factor. And dE dk inverse dE dk inverse is just equal to A over h bar times the velocity, and that is equal to 1 over gamma 1, 1. I guess I gotta, it's actually equal to this. 1 over A times A over, so it's times the 1 over A, which I'll pull out front. And so this is equal to 1 over A integral dE over 2 pi 1 over gamma times this GR gamma squared, that's my F, and finally the electron density due to injection from the left is equal to 1 over A integral dE over 2 pi GR J comma 1, I'm going to write out all the indices again, gamma 1, 1. Again, writing my GR squared is GR times the GA, so GA, because this allows me to keep all my indices nicely in order, 1 comma J, F, E, R, J comma 1 star. I just unfolded my GR magnitude squared into a GR GA, where GA of 1J is equal to GRJ1 star. And I do this because the indices then become cyclic. And this is the way it's written. And this is the way you can keep track of your indices. So it starts with J, it ends with J, and it gives me my N sub J. And as usual, if you want spin, you got to multiply by 2. So if we want spin, we'll throw in an extra factor of 2 for spin. That'd be for our spin. And we go through the same exercise for the right-hand side. So if injection from the right, I don't know whether it's a laptop or the projector doing that. I'll try the other laptop after the break. If we inject from the right, then we just have Nj right is equal to 2 over A integral dE over 2 pi we're injecting from the right. So if we inject from the right, J comma 3, and the rest should be obvious. Gamma what? 3, 3. And then GA what? 3J. When you do the indices like this, it's really powerful. F minus the chemical potential of the right contact, E minus mu R. And of course, the total electron density is the sum of the two. So what we're really after, that's nice, but what we're really after is just N sub J. So N sub J is just summing up Nj is equal to Nj left plus Nj right, and that's equal to 2 over A integral dE over 2 pi GR J1 gamma 1 1 GA 1J F of E minus U left plus GR J3 gamma 3 3 GR 3J, I mean GA 3J, sorry. GA 3J times F of E minus U right. So that is the expression that you will see. It's a standard expression for the electron density in the device. In terms of the green functions and the gammas.
I don't understand, but when we are calculating current, we are just only considering left or right, either one.
You know, taking the difference. So this really, you can think of it as, you know, injected from the left minus what's injected from the right. So you have current going both ways. Your contacts are injecting, and the sign of the current is going to depend on which contact is injecting more, because the transmission is the same for each energy. So again, it's just going to depend on which Fermi factor is greater. Whether mu left is greater than mu right is going to determine the sign of your current, which that's also the sign of your bias, so that's good, right? You want current flowing in the direction of voltage, not against it. But the physical picture is you've just got these contacts injecting current. You know, current has a sign. It's like a vector, whereas charge is a scalar. So the sign is determined, so you take the difference to determine which direction the current is flowing. But the density, you just sum up. They're both contributing. There's no difference involved. They both contribute to the density in the device. All right, let's take a break.